Right. So yeah, what I'm gonna want to give you today is actually a very, very brief introduction to molecular networking and the GMPS infrastructure. And yeah, as probably many of you know, this is a very collaborative effort and with many people in the Dorstein lab, and most recently also a lot of people like outside the lab and within the community. So I don't know, I think this has really become a community-wide tool that is kind of like a platform where we integrate now different yeah, like smaller workflows and tools. And I just want to like showcase like some of them, but once you're familiar with them, there is actually an entire variety of like different things you can do. Hopefully we will have time at the end to like talk a little bit more, yeah, like interactively about some of the things. But what I really want you to be able at the end of the class is to actually submit some like initial molecular networking jobs and like explore the data a little bit on your own. So that's why we're going to start right away with the hands-on part. And because we are all on our computers, this should actually be super easy and fun. So I would encourage you to open your browser and actually type in, let me go to my browser myself, gmps.ucsd.edu. So, and then where you should get to is this page here, basically. And you can see at the top right, like I have already a user account. So if you do not have a user account, then you can hit here the register button and quickly make your own GMPS account. So I think it's literally gonna take you a couple of seconds. And if you have one already, just like sign in, and then you should get to like the main page. Can I get some thumbs up if you got there? Can be either in camera or yeah, emoji, perfect. All right, and then yeah. So the very first thing we're gonna do then is we're gonna scroll down a little and click here on Create Molecular Network. So once you're logged in or created your user account, and scroll down on this main page to click on Molecular Network. And then what should happen is that there should be like a page opening up with like such like an input document here. And yeah, we're gonna do like a very basic job submission of an initial molecular network. And once we submitted that, I am gonna tell you what this actually is doing. But it's gonna take like 15 minutes or so to be processed. That's why we're gonna do this right away. All right, so yeah, basically what we're gonna do here is first we give the thing like a title. So I choose here SIO 262 E. coli Nissl, because that's like some of the extracts we're gonna work with today. And then the next step is here we're gonna change the mass accuracy, because we're actually gonna use high resolution data. And in a second, I'm also gonna show you what the difference is there. And then most important, we're gonna select the input files. And therefore we just click on here, and then there should be a new window popping up where we can like select input files. And some of you may have already files in their user account. And if you just registered, obviously you don't have any files there. So that's why we're actually going to make use of some publicly available data. And I think that's one of like the really nice thing of GMPS, that it's not only like a library search tool and molecular networking tool, but it's also like an interactive environment where people can access other people's data and set this in context of different studies. And I think recently this really starts to pay off. So in our case, we're going to make use of E. coli Nissl data, which we acquired in the lab. And to actually import this, we're going to click here on the Share File tab. And then here a new window should like basically switch. and you see that there's this import data share field. And what we can do is we can just like type in a massive ID. This is basically the code for that data set. And then we hit import. And then when we go back to select input files, we should like basically have this data available. And to show you quickly how I got this number, so there's the massive repository. So massive.ucsd.edu. I can actually share this in the chat if you want to play around with this yourself. And here, you don't even need to log in. You can go and browse publicly available data sets. And that basically provides you a list with everything that is publicly accessible and massive. And you see, okay, Ming just uploaded a test file for something we want to show you later. But if you would here upload it by, I don't know, sort or like search for my name, then there's probably some data set for E. coli Nissl here, LCMS viewer example data set. And here, this number under it, that is the massive ID. And that's basically what I used to pull this data into my GMPS workspace to further process that. So again, I can also let's see, copy this in the chat. Oh, there we go. And yeah, then you could basically import that. So okay, I hope it's the same number. Yeah, perfect. So yeah, maybe just copy paste it from the chat to make sure that it actually works. And then once you hit import and you go back to select input files, then you should actually now below that field see like this massive data set. And then you can expand this and expand the 3 till peak. So this is basically the MZML files that are contain like the mass spectra. And then you can highlight them by just like clicking on them. Then they should like look like a little gray. And then you go up and click to spectrum file G1. So that would be for group 1. And then you could do the same thing with the 3 remaining files. And then hit on G2. And then on the right side here, you should see that those files are selected for you to see. And that grouping is actually important because that allows us later to differentiate between the 2 groups. All right, that probably was a lot of information. Who made it to that point? Can I get some thumbs up or thumbs down if there were problems? All right, I get some thumbs up. The very good news is if you did not make it and kind of get lost at any point, there's like a backup link I will share with you later. So you can also just make use of that backup job.
And we're also recording and it'll be posted on Canvas so the students can have access to, if they want to go through it a little more slowly.
Awesome. Yeah. And there's a couple of other resources I point you to. So yeah, I think like submitting this job set, that's probably very helpful, especially if you have already or planning to like analyze some tandem mass spectrometry data. All right, so let's assume we selected our files. Then we just hit here, finish selection. Then the window should close, the files are selected. And then all what is left to do for now is to put our email address down here at the bottom left, and then hit submit, and then the job should be running. And once it's done, you should get an email and with a link, and it says, yeah, like your data analysis finished. All right, and now if you wonder what we just did, so yeah, I was not 100% sure what the starting point for all of you is. So who has used mass spectrometry or is like very familiar with mass spectrometry from you? Okay, can I get thumbs? Almost everybody. All right. So then for the thumbs that are missing, another take-home message from this course is that, yeah, mass spectrometry is definitely, I think, a very simple analytical technique because it just measures mass of ions. And that's also like one of the caveats because we measure mass per ions, means that we can have single or double or triple charged ions, and that actually implicates the mass that we measure. So here, very important, mass spectrometry displays the mass of individual compounds as ions, as mass over charge. And that for small molecules most often is not super important, because we always have, well, most of the time have charge stage of 1. But like if we deal with proteins and stuff, then maybe later that becomes like super important. All right, and yeah, as I said, I think it's a fairly simple approach. All we do is we ionize molecules and then separate them by their mass, and then display this like different mass units versus their intensity. And then what we would get is such a mass spectrum. And then we can basically say, okay, this has 200 Daltons, this 300, and so on. And now to give you like a very brief idea of such a mass spectrometer, there's a couple around at Scripps, so you probably have seen some. Yeah, it basically is built up by like this mass analyzer, which I just showed you. And another essential part would be like the inlet and ion source, as well as like the vacuum system and the detector. So now, in terms of like different, technologies, what is there? I think you have a Q-top at Scripps, and I think what I just showed you, that principle where you basically accelerate ions and like separate them over like a certain like drift space, that would be time of flight mass spectrometry. So this is one we have in the Dorstein lab, where we actually have such a flight pattern. It's basically the principle I just showed you in this animation. Then here in the very front of this mass spec, there's actually a second mass spec, and that's a quadrupole, which is kind of like a different analyzer, and in some instruments it's combined to like pre-isolate ion packages. And in a second, I'm also gonna tell you what this is very useful for. But here we basically do not separate ions by like a field-free drift tube, but rather in a kind of like ion trap, where we have 4 poles that have like a polarity, so they're charged, and then depending on your polarity of your ion, they're gonna fly towards one of the rods with the opposite polarity. And now if you like switch them really quickly, what would happen is that they kind of like always follow the opposite polarity, and if the frequency of the switching is right, we'll never reach it. So they kind of like spiral through that thing. So, and the main difference here is that this is kind of like a scanning type of mass spec, where you basically can vary this frequency and then let different masses through. And that makes it really interesting to not do like full readouts like with the TOF, but to actually set this to a given mass and use it as a kind of like filter. And that's why this thing is often used as a kind of like pre-filter in hybrid mass spectrometers. So a QTOF would be one of those. So that's a quadrupole time of flight mass spec. Or here in an Orbitrap, for example, which is more the high-end type of mass analyzer, you would have like a quadrupole filter here at the beginning, and then here ultra high field Orbitrap mass analyzer. And here you basically have a different type of like mechanism. You have like central electrode and ion packages surrounding this, and this up and down movement basically is dependent on their mass. So here, really interesting, the detection principle is now based on a plate detector. So here you have kind of like 2 plates, and like as the ions cycle around, they induce a current, which you can record, and then with Fourier transformation, you can actually calculate a mass spectrum out of this. So why I showed you this 3 different types, there's a couple of more, but I think those are like kind of like the interesting ones we have in the lab, is that they all have like different characteristics. And so depending on your application, you may want to like pick one of those. And just to give you an idea what is important, so like resolution and accuracy is like very important if you want to like use this for like structural determination, for example. Then sensitivity, linearity of the detector is really important when it's about like quantitative analysis. So here, the TOF, for example, is not doing great, but the quad, or especially a triple quad, are like doing very well. And then the scan speed, so how many spectra can you actually acquire? this becomes especially important when we're talking about like non-targeted analysis, and we actually want to like identify as many molecules as possible. So here, I think it's really exciting because we're in a time now where those machines get like really fast, and we can actually acquire thousands of spectra in a single LCMS run. All right, and then ultimately the cost, I guess that's especially interesting for the PI level of the discussion, and once it gets down to actually buying such a machine. But yeah, here a quadrupole, a single quad would be way cheaper than like an Orbitrap, for example. All right, and how does that actually look? So here, especially resolution, I think is a kind of like key thing. Here, I plotted like a typical mass spectra when you zoom in from a quadrupole, and you can see, okay, we probably get like a more or less like resolution around like 0.1 MZ or so, and then the accuracy is probably also in that range. So obviously, if you would now calculate a molecular formula from that, there would be many different possibilities of atoms that could basically like fit in that window. So now if we compare this to an Orbitrap spectrum, that's of course way more accurate. So here in red overlaid, you see it's like very precise. So here we have probably, if we internally calibrate sub-ppm mass accuracy, and for example, calculating the molecular formula of your new isolated natural product, that of course helps a lot. So here, accuracy is really what you want. So now the other thing is like, how do you ionize this stuff, and how do you like get actually like your molecules into the mass spec? And I just want to show you one technique really quick, which I think is like probably the most common for natural product research and like more larger molecules in like a liquid phase, and that is electrospray ionization. So here we kind of like have our compounds like in a diluted in a solvent, and then we infuse them in our source together with like a nitrogen like stream, and there is a potential between like the tip of that needle and here the inlet of the mass spec. And then basically what happens is that the charges within our like little droplets that kind of like spray out here kind of like get closer and closer to each other as the droplets shrink within that nitrogen stream that often is also heated. And then they become so small that they're actually kind of like expelling each other. And then you kind of end up with like actual single ions at the end. So there's a couple of interesting basic research on that, but I think roughly that is like how it works. And I think this is really exciting because that is typically the ionization technique that is used to couple mass spectrometry and liquid chromatography. And that is, of course, really helpful because now you can first decomplex molecules here on a column and then kind of like get a readout and like measure the mass. And then besides your chromatogram, you would have an additional dimension where you can actually directly see the mass. And I mean, if you've used this already, you know that comes in really handy when you like, try to like characterize unknown molecules from your extract or whatsoever. Now you probably also know, and we kind of like spoke about that already with regards to like the resolution, that of course like a certain mass can have like multiple elemental composition depending on the accuracy you measure this with. And certainly there can be many isomers or many different compounds that all have the same molecular formula. So often this is really just like the first step to annotate or like to solve the structure of an unknown compound or to dereplicate this against other already known compounds. So that's why, and I think that's been around now also since probably 20 years or so, the use of tandem mass spectrometry has become like really an essential method to like get an additional information from a mass spectrum. So the idea here is that besides that initial separation of molecules by their mass, we kind of like isolate a certain species, a certain mass, and therefore we would use typically a quadrupole. As I said, it's good to isolate different ion packages, and then we activate them in the gas phase, most commonly by collision-induced dissociation, and then basically make those molecules fragment. And then we do a second mass spec analysis where we now basically scan for those fragments. And that is really exciting because dose fragmentation is typically according to the structure of a molecule. So here, the weakest bond would typically break. So if you have a peptide, that's typically like the amide bond. And if you have, well, some other interesting molecules, it's typically like the weakest bond. So you can like make sense out of that and use this to, yeah, basically propose a structure de novo, which is hard. And more commonly, you can use this fragmentation pattern to actually record the spectrum in a spectral library and then simply match your experimental spectra later on against this library. And that is a big part of GMPS. So the GMPS library is basically a user-based library where all of us can annotate our molecules and then make this knowledge like available to the community. And seeing that grow over the last 5 years or so is really something amazing, because from like initial annotation rates of 1%, we can now annotate 5 to 10% of the molecules we typically detect. And that to me is like a tremendous like increase. Of course, that needs basically all of you as a community to annotate the compound. So once you published your new molecule, why not like uploading the MS2 spectra you acquired to like this library and help basically others save months of their PhD work to solve the same structure as you have just published. So now I mentioned already, we can basically put this in a library, and we can annotate now 5% or so of those molecules. That of course is like still leaves us with 95% of the compounds typically unknown, which is of course still like a problem. But now there's a couple of possibilities to not only match exactly the same spectra to the library, or our spectra to exactly the spectra in the library, but also broaden that search a little bit. And that is kind of like a spectral similarity search. So this is based on the basically ground assumption that if we have here a molecule, and let's assume here the CC bond would actually break, then we would obtain 2 fragments, the yellow one here for the C terminus, and then the green one for, well, the other C terminus. So now, if we would assume maybe there is a modification at here, like that fragment on the left for, let's say, like an methyl ester, for example, then we would assume that the green fragment should still be the same, but the yellow fragment and the precursor mass, so the intact mass of the thing, should be shifted by exactly the mass of this modification. And that is now the really like key point of the spectral similarity search. So if we now compare 2 spectra to each other, and they do not exactly match, but we allow that the mass difference between like the precursors, so here was marked with asterisks, would also be allowed for all fragments to be offset. See? Exactly. So in this case, by 14 m/c, then we could actually start matching things that have like modifications. And this is exactly the basics of molecular networking. Because now, besides this expanded search between 2 spectra, maybe our experimental spectra and the library spectra, we can also do this between all experimental spectra within a sample. So yeah, here we would basically take everything we recorded and then pairwise align them to each other, and then depending on the score, what we obtain, establish connection between those spectra. And then we can represent them as nodes. And what you would get is basically molecular families of, well, related MS-MS spectra. And because we assume that similar structures will result in similar spectra, we should get basically networks of similar molecules. And that is really nice, because now we can explore our data, and basically molecular families should be kind of like organized together. And maybe one of those, like here the center one, would have like a GMPS library hit. Then we can propagate this annotation to the surrounding nodes and say, oh, this here was actually a bile acid. So I assume that this is a family of bile acids. And then as a chemist, this is of course like really exciting because we see the mass difference between those nodes. And then we can start thinking about, okay, what could this actually be? Maybe we can also start looking at the actual fragmentation patterns. And then in this case, we see, oh, that's actually here for like this phenyl rest. So maybe we have a substitution of this amino acid. And then there is another delta, which actually corresponds to oxygen. So here, maybe that could be to correlate to substitution with tyrosine, and so on. So this is pretty much the basics of molecular networking. And I hope that by now the jobs we just submitted should all be finished. And then what we're going to do for the rest of the class is we're just going to explore some data and actually find new molecules. Does that sound good? Did you get the jobs back? Awesome. That's great. So yeah, the data we're going to talk about now is, as I mentioned already, from E. coli Nissl. And the really interesting thing about that is that we had a knockout mutant for the Yersinia bacterin cluster. That's why we separated them in those two groups, because one was the wild type and the other one was here a deletion of the Yersinia bacterin cluster. So we try to confirm that basically this molecule is made by the biosynthetic genes of this cluster, which maybe comes handy to one of the questions you have in your own research. And yeah, there's preprints where we actually use this for some other stuff if you want to read more about the details. But most importantly, there's this URL here, and let me also paste this in the chat because I prepared a little document for you where actually all where all the links for what we need for the rest of the class are located. And now, if I open this in my browser, yeah, I should get to this Google Doc here. And then, yeah, there's basically two objectives. So first, we want to find new Yersinia bacterin derivatives. And then we also want to compare the wild type to the NRPS knockout strain. So, and then for the first one, you can just click on this link, or if your job actually finished and you want to work with your own data, then you can just click on that link in your email. Okay, I'm going to use this one. And then what you basically get is here a kind of, yeah, final like job. There's a lot of different links. And I think as you become more familiar with molecular networking, you might want to appreciate some of those functions. But the very, very core information we're going to talk about is that cluster view and then this browser network view. And so here, if you click on view all clusters with ID, what you will get to is basically a list of all molecules or all ions that were detected. And you see it's 1,698. So there was a lot of different ions detected. And then we could start exploring them. And as we know already that Yersinia bacterin is here, we can simply go here to this library field and type in Yersinia bacterin and then hit enter. And then what you should get is all nodes that actually had a library annotation of Yersinia bacterin, or here the Yersinia bacterin iron and copper cluster. So now you know already that that's actually a cytosol. But let's speak about Yersinia bacterin for now. So here that would be the first hit. And if you click here on the left on view network, then you can actually open this inside of the browser and you get to this network view here where you can start already like exploring the chemical space around it. And what you see here is that the blue dot is basically Yersinia bacterin that's annotated. But now if you click somewhere in the field, you see that there's actually more nodes. They all have like this number. So this is simply like the cluster number. But if you click here on the left on parent mass, then you actually would get the molecular weight. And then you can click here of delta MZ and you get the mass difference between like the different nodes. And then we can already start basically exploring the thing a little. If I click here with left click on Yersinia Bactin, it will display here the mass spec. And if I click with right click on a neighboring node, then on the top, on the bottom field here, I would get the other mass spec, and I can then here click on this magic stick and actually get the labels for it. So I see what masses do the different fragment ions have. And well, here we have a mass delta of 2, so that's probably like a double bond somewhere. And we can, yeah, basically start exploring this. And I think if you have a new molecule and you see directly like the space of other derivatives around that molecule, that's of course like a really helpful information. So now, and I hope that Ming joined us, because I invited Ming as a special guest for this, because we want to showcase one of the new tools. Is he in the list? Yeah, Ming, why don't you take over here and actually showcase the LCMS viewer?
Definitely. Thank you, Daniel. So Daniel showed you how to interactively play around with these networks, but I'll have Daniel keep the slides up. But one of the things that you can do as part of this hands-on as well is, instead of clicking View Network, as Danny did to bring up the network, actually, wait, oh, no, there you go. So Danny has a little follow on here in the slides. But yeah, you can click Cluster Spectra under this Yersinia Bactin. And what this does now is it'll tell you what files and what spectra are actually coming from where that node came from, where that molecule occurs. So once you have that kind of information, it's, when you look at these networks, they're a little bit abstract, but one of the things we want to do is connect it back down to the actual raw data that you put on the instrument. And so if you click on that, it'll give you this new table, and every single entry here is actually from from that molecule from your actual data. So we'll just click on this very first link here called View LCMS Chromatogram Beta. So yeah, Daniel. And so what this does, this is something we've been doing the past couple of months just kind of for fun, and we think it's a little bit useful. But one of the kind of things historically I hated is anytime you want to go back to your raw data, you would have to go open some vendor software, or you could download the data, open vendor software, and that was kind of a pain. So here it's a single click away. It's all in the web browser. You can interactively explore the full LCMS chromatogram, or in this case, it pre-populates the M over Z of that particular molecule that you're seeing it back in this case. And what we can see in this bottom right panel is the XIC of that particular molecule. And so one of the interesting things about this particular molecule, and Danny can speak more about the analytical chemistry portions, is that you can see two distinct peaks here, which seems to indicate that there's two isomers of Yersinia Bactin that could elute at two different times. But one of the interesting bits is in the actual network, for this molecular network you generated, it only appears once. So one node, so we think there's only one version of it. And so this is an artifact of this classical molecular networking, only looking at MSMS and saying, hey, we don't care at all about the retention time. It's a nice simplifying assumption, but it sometimes oversimplifies. And so in this particular case, we see that it missed out on two different isomers of this particular molecule. And number two, it doesn't take into account and calculate the relative abundance. So what it does in terms of saying it's in one sample versus another is more of a presence-absence from an MSMS perspective, which again is a relatively good simplifying assumption. If you care about presence and absence, and if you're doing knockout experiments, probably like Danny was doing, that's perfect for the most part. But if you want to look at more subtle changes in abundance, then you want to be a little bit more quantitative by integrating these peaks. And so that's one thing this LCMS browser will help bridge, is the networks where it's just qualitative comparisons between groups back to the raw data, and just inspecting and making sure, are there different isomers? How quantitative can we be? And then so Danny will take it up from here on how we can hopefully rectify some of these issues, both in terms of new pipelines and software, and then later on, kind of letting you explore in another fashion. So hopefully that was less rambling than it seemed, but I'll let Danny take it from here.
Awesome. Thanks so much for stopping by, and yeah, especially thanks so much to Ming for actually like building this new viewer. I think this is super helpful, and yeah, I love it, and I hope that you will also find this helpful because it does not require you anymore to actually install some vendor software on your computer, but you can like explore this data all in your browser. And the very handy thing, that link you just clicked on, I created for you, but that way you can actually create views for, I don't know, your coworkers or collaboration partners, and all they need to do is click on it and they can actually see the raw data. And in this case, I think this is actually really important because it shows that we missed like here the difference between like those two potential isomers. So again, here in this XIC view, which stands for extracted ion chromatogram. So we basically take here only one MZ value and plot a chromatogram out of that. We will see that for the mass 482, we have 2 peaks. But if we go back on, let me see if I can go back, on that network view here, you see that there was only one node with the mass 482, right? So now the question is why, what happened there? And I think this is one of the inherent disadvantages of classical molecular networking, that we have like multiple MS2s over the course of an LCMS run. So in order to like deal with that redundancy, what we do is we cluster them. So yeah, if you go a little bit more in the detail about the theory, so when you come from your LCMS file here on the left, the very first step before actually constructing this molecular network is that all identical spectra are collapsed together and then represented as a node. And then we can use spectral counts as a proxy for relative abundance. But in a case where you actually have like 2 isomers, like for your cinyabactin, so those are like diastereomers, so we can actually separate them by chromatography, but they will resolve in the same MS2 spectra, so you may miss out here. And yeah, here I think this is really important. This is a really good example for like the importance of inspecting your data later on. And I hope that the LCMS viewer will make this now a little bit more easier. Also, if you want to expect somebody else's data, as we did over the last couple of weeks from actually a couple of papers that made their data public. So there you can also just pull this into your browser visualization tool. However, why I thought this was a really good example to showcase here is because I think this is a very good reason why, besides classical molecular networking, for those of you who are like familiar with this and want to like go to the next step, I really recommend to actually start using feature-based molecular networking, because this combines a chromatographic data analysis as a first step. With here, we support a bunch of different pre-processing tools such as XCMS or MZMine, which are all open source, so you can download them. And then you can actually first integrate your chromatographic peaks and then create consensus MS2 spectra from there, and then create your molecular network. And what that does is that it actually resolves like different isomers. And that's the other advantage. I think it has a better proxy of quantitative information. Yeah, that's another like development together with Louis, Ming, and Robin, and yeah, the entire GMPS community. We just published a couple of months ago, and yeah, this is available. So yeah, if you haven't used it already, then I would encourage you to give it a try. And now, yeah, when you actually go back to the document I prepared for you, then that second link is for the feature-based molecular networking data analysis of this very same data. And when we now click on that, what you will actually see is that now indeed there's 2 Plu nodes, which when you label them with like the parent mass and so on, you see, okay, they're both 482. So here, indeed, we can now resolve the isomers of this particular compound. So now, okay, that's for the feature-based molecular networking, but we want to explore some new molecules. So as a probably next step, and maybe later on also, as if you want to like play around with this already at home, feel free to explore this. So one very easy way is to simply like again click on those molecules, and then you can like look at the pair, for example here 468 and 482, and then like display them in here this view. And again, with like clicking the this magic stick, you can actually annotate the masses. And then what you can see if you zoom in is that some of those ions are actually like constant, and then some others might be shifted. And then for Yersinia bactin, as we know already the structure, we can start hypothesizing potential fragmentation mechanisms. And then as we have here, most of those fragments that I could explain here with like certain bound breakages. So if you throw this molecule into ChemDraw, you can actually start like drawing like lines in there and calculate what the weight of those fragments would be. And then what you will find out for this example is that most of the fragments we could explain here on that C-terminal, N-terminal part are actually like constant. So the modification in that case, I think it's 14. So that could correspond to a methyl group might be located at the C-terminus. So that I think is a very good first hint for like a potential structure. And Bill, I think that kind of group reminds me actually a little bit about leptochelium. I think you and Carrie looked at that recently. But anyway, so I hope that this seems like a useful tool for you, and you can actually like start exploring new molecules after you dereplicated the already known ones. So now again here also for feature-based molecular networking, we support a few through the LCMS viewer. So here, if we go back to that link thing, I actually provided you a direct link out for the LCMS dashboard of this particular example from the feature-based molecular networking. And when you click on that, you will see that now, in addition to that one file, which we visualized for like the classic molecular networking, here I'm actually making use of the two groups here. So there's basically multiple files in each of the group. One would be like the wild type, and the other one would be the knockout. And that is really nice because now when I set here the XIC, the mass for the XIC, and the retention time window for the integration right, I can actually already directly generate a box plot in here. So now, what we see here is basically the groups, and surprise, surprise, orange one is our knockout. And then if we scroll farther down, what we would see is here, okay, we see that there is a clear difference in relative abundance. So now for the knockdown, obviously it's obvious, but let's say we would play around with like some like promoters, or we would play around with signaling, or like a certain phenotype response, or response in phenotype. Of course, here like tinier differences could be like really exciting, and then having actually a box and whisker plot is of course way more accurate than having spectral counts only in your pie chart. So yeah, I think that leaves us only one link left in the viewer in the document here, and this is at the very bottom, the link to our workshops. So if you click on this, let me go to my browser. Yeah, this will basically bring you to the GMPS documentation page, where I think for like all the tools we have is a detailed step-to-step tutorial available. But here you can also see that we have upcoming Zoom events where we actually like talk about particular workflows more in detail. So the next two are actually about feature-based molecular networking. I don't know who speaks Portuguese from you, but that could be interesting. But when you scroll down here, you will see that there is a list with all past workshops. And the cool thing is that for many of those, we still need to add it for the LCMS browser workshop, but for many of those, there's already a link for video. So here you could actually look at recordings of like all like this different workshops and tutorials we did. And if you missed, for example, some of the things we showed today, then you could go for classic molecular networking, click on the link, and then it brings you to YouTube. And I don't know who did this. I think Emily, Morgan, and Ming. You could basically go through like the step-to-step guide of the of like the particular workshop. So we did this for feature-based molecular networking and for ion identity networking, which I think is a very exciting tool as well, especially if you want to like look for like different ion adducts. So yeah, there's a lot of material. Then besides that, here on the left, there's the kind of like general documentation. And here, besides the brief introduction, there's also detailed step-to-step tutorials, for example, for feature-based molecular networking here under advanced data analysis tools. And then if you decide to use, for example, Enzymine, you can go there and there's a step-to-step tutorial, including some videos as well. We recorded how to actually process your data. But this is, I think, if you want to like really bring it to like the more advanced level. I hope with what I've shown you today, there is like enough like information already to at least start looking at your tandem mass spectra in like a new way and more systematically make use of like that amount of information. Because obviously, if you go through manually through like thousands of spectra, I think that's far beyond accessible anymore. So you need some type of like software aided tools to actually completely mine this data. And to me, molecular networking and GMPS are definitely a nice way. And I don't know, was I think a game changer to many people in natural product fields. So I guess with that was the kind of like presentation part. So now I don't know if there's questions or discussions. I think it would be cool to use the rest of the time to actually talk a little bit about particular needs you have, or I don't know, ideas you have, and maybe I can point you to like some of the resources we generated.
Thank you so much, Daniel. That was awesome. Yeah, let's definitely open it up for discussion or any questions that everyone has. I was blown away. I'll definitely be rewatching this video. So.
Hi, Daniel.
Hey.
It was a really great lecture. Really enjoyed it. I have actually a question I had for a long time. You mentioned this phenomenon that occurs in classical molecular networking when I have two isomers with exactly same mass but different retention time, and they are kind of clustered together and produce one node. But nevertheless, I have some information on retention time when I review my data in Cytoscape or whatever. Yes. Which retention time is actually displayed? The first one when the first molecule occurred, or
no?
Is it?
This is a very good question. So that is a very good indicator of where you actually have isomers, because there's two values you get, and I think the retention time which would be displayed is the average. And maybe, am I still sharing my screen? Yes. Let me go and open my browser. So yeah, let's just, and maybe you guys can like do the same thing to follow. So if I click on that first link, open my classical molecular network, and then I would go on this cluster with all ID. There is the RT mean, right? And when I now, let's just click on a random network.
Oh, that's a good one.
Yeah, there's this cluster network view, right? And then I basically see all raw MS spectra that contributed to this cluster, so to this collapsed molecular network. And now there is actually an RT, right? Because this is the retention time of a particular scan. And if I now see, okay, they're all around 120 seconds, then most likely there is not much variance, so that's probably only one peak. And we can actually now click here on the LCMS viewer and like visualize this. Let's see how it looks. But in that case, I would assume it should be one peak. All right. I assume everybody did it at the same time. So yeah, it takes a little. Okay, right. So here we see that there's one main peak, and it's relatively bad signal to noise, so it's probably low abundant compound. But in at that case, yeah, I would assume, yeah, here it's only one peak, and then if there's like other molecules, then they may not have been derivative isomers, but they could simply be isobars. And I can now update the mass accuracy here, and then I should probably only get a few. Yeah, but I think as a rough yeah, suggestion, that's what I would do. Yeah, see,
yeah.
So here it's only around 2 minutes, one peak. So yeah, basically go from your network view through like the actual clustered spectra. So and you click here, and then you see that, you know, okay, they're all like in the same range. So if I go back and actually do this again for Yersinia Bactin, here, let's see, then we will see, click on it, on the cluster spectra, that there is some type of variance. See here, it's 400 seconds, and then there is one with 460. So that's 60, that's 1 minute of difference in retention time. And if you see like this wider range, then it's an indicator that there was probably like some isomers. Again, just clicking on the LCMS browser now will allow you to have only like one click to do to actually inspect the chromatogram. And yeah, I think this is very helpful.
That's great, Daniel. I didn't know about this.
It's brand new. I think it's, yeah. I don't know if Ming is still here, but I think we started working on that like a month ago or 1.5 months ago. So yeah, you guys are one of the first people to actually try it. All right. If nobody has questions, may I ask a question? Did you find any exciting masses in that molecular network of Yersinia Bactin? Okay. Because there's a couple of truncated versions, I think. I'm not actually sure if they were connected in there. And yeah, one was just like recently described. There was, I think, a paper on just truncated Yersinia Bactin derivatives. So yeah, kind of like in every, I think, data set or every extract, I think to a certain degree, there's still like novelty in there. So I think it's really exciting to mine already existing data, actually.
kind of hoping some students will have questions, but since it's been quiet for a while, maybe I'll just ask you to comment a little bit, Daniel, on, you know, when you're dereplicating, and, you know, you talked about different types of mass spectrometers, and how much of an effect is there if someone deposits data acquired using one instrument and you're using a different instrument? How much of an effect is that? And, you know, whether the data was in positive or negative mode, it seems like there's a lot of variables that might affect your ability to dereplicate. Can you tell us a little about that?
Yeah. Thanks a lot for bringing that up. So yeah, that is a very important question. So obviously, when you have like positive and negative mode data, it's really hard to match that, because I think first of all you will have an offset by the mass, which one is probably protonated, the other one is like deprotonated. So that there's already some differences, but also in the gas phase fragmentation, I think there's just like differences. So I don't think that it makes sense to match positive and negative mode data. But most of the data is, I would say, acquired in positive mode, and then within that realm, I think it definitely makes sense to, and it's definitely possible to compare spectra between different platforms. So fortunately, most mass specs use collision-induced dissociation. So like the gas phase fragmentation mechanism generally is the same. So now, unlike in GCMS, where I think the community standardized like this electron voltage to 70 electron volt, which is kind of like the standard value, the energy for CID varies. So here, people like use their kind of like own values a little bit, depending on how well their molecule fragments. But also here, I think there is some kind of like default values. So we typically use around like 35% on our Q-Exactive platform. And I think most of the people in the community probably are within a similar range. And here, I think we definitely can also compare MS spectra that are acquired with like a different like collision energy. So they might not be like perfect matches because like the abundance might change, but I think like the main fragments still remain the same. So nevertheless, I think the more people would annotate actually a spectrum that is acquired at like also like a different collision energy, of course, the more likely it is that your spectra is covered. And when you look at like redundancy of like the same molecule that is actually annotated in GMPS, for example, for surfactant, then you will see that there is actually many spectra that were acquired on different machines. So I think here also just like expanding that organized knowledge is really important, and that increases the chance that your experimental spectra is covered. It would be nice if we as a community would reach like some type of, I don't know, like agreement for certain voltages to use. That of course would make it easier. And I don't know, systematic approaches like the NIST library, that is a commercial product, they simply measure all like the compounds at different collision energy. So then they have it at like 20, 30, and 40%, which I think is kind of like roughly the range. And then hopefully this will basically like help to cover the right setting for you as well. And then with regards to instrument platform, there is only one difference, I think, that is important, and that is the mass resolution. The mass resolution and the ion trap versus beam type CID instrument. So if you have think like the Amazon, the Bruker Amazon ion trap in the Moore lab, for example, that is like tandem in time. So here you trap and fragment the ions and read out the ions like all in the same space. But those mass specs are typically not very good to maintain like the low molecular weight fragments. So there, when you like compare, let's say a peptide, then you will see that like a QTOF, which is like a beam type MS instrument, will have like more prominent ions like in the low MZ range, and those might be missed in an ion trap. But here again, what this will result to is simply that the score of your matching will be lower, because in the low MZ range you still have like matching ions. So you probably can still like identify those. It's just you have to like lower your cutoff a little. And then another important thing is the mask accuracy. So at the very beginning, when we submitted that job, you saw that we changed the mask accuracy to 0.01 MZ. That was for high resolution data we acquired on the QXactive. So if you as input have low resolution data, then you need to make that that window larger. So then I would use like the default settings, which are, I don't know, like 2 MZ or 1 MZ, something in that range. Actually, if you are in the, I can share my screen again. If you are at the, let's quickly go back there. If you're here in this submission form and you hover over the field, I think it should actually, yeah, pop up this little box and explain you what values are appropriate. So yeah, in case you forget, but yeah, roughly, I think you should be aware whether you have unit mask resolution with like an ion trap or like a quadrupole, or if you have high resolution data like with a Q-top or Orbitrap, and then set those settings accordingly.
Daniel, some of my lab mates have been doing a lot more GCMS lately, and I know there have been plans for GMPS to integrate some of those workflows. Can you talk a little bit more about that and the future and promise for that work?
Yeah, so actually that was also just published a couple of weeks ago and is available now since a while. So you can do molecular networking with GCMS data. The thing is, with GCMS, you do not really have MS-MS, but a type of like all ion fragmentation. Right, so you kind of like constantly fragment everything, and because your chromatography is like so good in GC, you kind of like always have like baseline separated peaks and everything is like very sharp. So what that basically means is that you get a fragment spectra for a single isolated compound, but it's not MS-MS. And what that means is that you need to kind of generate like fragmentation spectra out of this data, and that's a process called chromatographic deconvolution. So there's a couple of different tools you can use. I think one would be Enzymine. You can do as well like some pre-processing. And then there's a new tool, which is actually an online workflow that's called MS Hub. It's a machine-based learning approach. And yeah, then you can just upload your data and process it right in GMPS. And to maybe show you quickly where that is. So if you go to the main page, then there's this data analysis, and then you just scroll down, and then there's GCMS, electron impact data analysis. And yeah, here, if you decide to do the deconvolution process online, then there's an MS Hub workflow. So here, you can just open this, and then you basically pre-process your things here to then go to the second step of a library search and networking workflow for the already deconvoluted data. And yeah, it's all within that realm of proteosafe workflow. So it looks pretty much the same, just like you have different settings to yeah, fill out. And it's there's probably a little bit too much to walk you through. But if you click here on documentation, you come back to like that page I showed you initially. And then also for GCMS, there should be, let's see what it is. There's also detailed documentation. All right, if you have a hard time finding it, like I do right now, if you go to GMPS Analysis Tools Overview, then there should be also a link here. Tool index, excuse me. Let me share this in the chat with you too. All right, and here you basically have an overview of all different tools. And then if we go to GC, so yeah, here, MS Hub GC deconvolution. Oh, there's no link for the documentation. Uh-oh. That we still have to put in here. But somewhere there should be documentation here.
Awesome. That's really exciting. Hope some of my lab mates will be able to use this. One more question out of curiosity. I remember there was always a bit talk about like just the amount of data being generated and also stored, and with the plans for expansion with GMPS globally, like how is your lab handling all of that? Just briefly, can you talk a little bit about all that data storage?
Yes, here I found it through the search function. I will paste it in the chat and then also again the tool index. So data handling. So fortunately, we're like working closely with the CCMS. So that's the Center for Computational Mass Spectrometry. And they are actually hosting Massive. So that initial page here, what I showed you, this is basically the Massive environment. And when you click again here on browse all publicly available data sets, then you will see that some of them have like this GMPS tag, but actually many of them do not, and they have like this PXD number. And that means that they're like proteomics data sets and are shared through Proteome Exchange, which this was actually built for. So we're kind of like making use of, yeah, like the proteomics community data repository. And because there's, I think, way more people doing proteomics nowadays than metabolomics, there's definitely like huge storage capacity for their data already. And GMPS, because we work closely with the Bandera lab, we're making basically use of that infrastructure. So yeah, GMPS kind of sits on top of the of Massive. So that's the one of the mass spec repositories for the proteomics community. Does that answer your question, or did you also refer to like local storage for me as a researcher?
No, that was really it. Just the data storage for all the public data sets.
Yeah, I mean, from a practical day-to-day usage thing, we also have a NAS system in the Dorstein lab. I know UCSD has like different servers where you can like, I don't know, have like kind of like external storage. I typically have a backup on my computer, then one on our local server, and ultimately I really try to like upload my data to Massive relatively fast, because I think that's from all the places I can put data probably like the safest, because that's in the like UCSD Supercomputer Center, and that is like double backed up. So that should not there should be like a very small likeliness of any like data loss here. You don't have to make this data public right away. So like I often upload data sets and then I just keep them private, you know, and then once it's published or once I know, okay, this is actually important and I want to share this, then I just like hit make the make public button, and then it actually like appears here. So yeah, I think this is really useful just to have like this storage space. Making it public, not only your library spectra, but also your experimental spectra, your full data set. I think this is really useful too. And I don't know, the class ends at 4:50, right? Maybe one thing I should show you is one of the repositories tools we work with, where you can actually make use of like this public data. So because right now we're talking about like dereplication with the library, right? So you can match your experimental spectra against the library. So if, I don't know, Trevor uploads his new molecule and I find the same thing, then I can annotate them and send him an email and say, thank you, saved me some time. But I could also match this molecule to actually his raw data in case he uploaded this to Massive and made it public. And there's a tool called MAST, the mass spectrometry search tool, accordingly to PLAST, that actually allows you to query a single spectrum against all that public space. And that is particularly useful if you want to set your data into context of different environments, for example. And yeah, to highlight this, so that link I posted for like the tool index. Let me see. All right, now I'm lost. Yeah, this tool index here, it's in the chat in case you didn't find it. So what this like lists is basically all workflows. And now what you could do here is you could go to MAST, and then there is a GMPS link and a better link in case the GMPS link doesn't work. Then you can just hit that workflow, and then you will directly get here. And what you could do here is simply, I don't know, do like a test mask, and then actually paste in the list of your spectrum. So this is kind of, yeah, a little bit of manual thing. So once you have like actually a spectrum, you can simply like export all ions with their intensity and then paste this in here and then search this. Because this is not really useful in terms of it's not really user friendly. There's also a different way to do that, and this is right from your data. So let's go back to actually one of the jobs I submitted. So here, okay, I'm back here at this network, but if I click to back to status page here, then I should get back to that like initial view, right? And now if I go to view all spectra with ID, then you see that here on the left, there's already this link masked spectrum. And you see here on the right that there's already a couple of interesting molecules. Here, this is actually this truncated Yersinia bacteria I was talking about earlier. So now let's say I want to see in what different environments this might occur, right? So I don't know, to like add some like context of yeah, like ecological importance to that, then I simply hit mask, and then it pre-populates this yeah, field for me. So that's how it would look. So here you have your ions and your intensity, and then the precursor mass, and then I just need to give it a title. And here again, set like mass accuracy. Let's assume we want to deal with high resolution data. And then I just go down and hit submit. And then, well, it's probably not going to finish in the next 3 minutes, but now later on, you should get like a result back, and then it should list you the actual different data sets. And to show you how this looks like, let's see. So it's called Search Single Spectrum in the Workflow Manager. So I just went to jobs, and then I get like a list of like all the stuff I did in the last couple of days. And I'm just going to show you some masked spectrum like I did. So yeah, I was like looking at rosmarinic acid, which I think is important in the context of diatom bacteria interactions. So I got excited about that, and then I was masking this, and when I go to dataset matches, then I actually see the different public data sets in which this spectrum was found. And then, okay, that was probably not what I hoped for, but yeah, rosmarinic acid is definitely a molecule present in different food. Because yeah, when you look here at the names, they all say, okay, this is food. Now, if I would only find it in one, and if I would think that this is really interesting, I could actually dive deeper into that. So let's assume here, okay, that beverage thing, I'm excited about that. So I can just click here on this massive view link, and then it will actually tell me who uploaded that data. And in this case, it's Julia Gauklitz, a former postdoc in the Dorstein lab. And I could just like email her and say, hey, I actually found this molecule. And yeah, as leptoquilin is a very exciting compound, I think recently somebody from actually Portugal contacted one of my collaboration partners and said, oh, we found exactly the same molecule in our sample. And now it connected basically these two different groups working on the same molecule for which the structure is still not known, but maybe that enables now like some type of like interaction, and they can share data and maybe like solve the structure together. So I think this is a really nice story of how useful such like a repository scale tool can be, and how useful it is for you to actually upload your data and make it public to others. And yeah, I guess that's the story behind MAST.
Thank you so much. It's so in-depth and amazing, the work going on at GMPS. I didn't know about that tool. I haven't seen that. That's really cool.
Yeah, so there's a bunch of different tools. So it really makes sense to like browse through that list I shared with you. I can do it again onward. Okay, I opened too many tabs. Yeah, the tool index in the chat. So yeah, there's a couple of useful things. So like the main things, molecular networking and feature-based molecular networking. I think those are like kind of like the main workhorses. Then yeah, there's a merge polarity workflow where you can actually merge networks from positive and negative mode. Then there's a bunch of like different in silico annotation workflows, and yeah, a couple of other like data analysis tools, which I think really, so that's what I meant with at the beginning, that GMPS really has become a community effort and mainly serves as a kind of like platform where you can use different tools. And yeah, I think it's worth to go through and like look what those different things do. Or I don't know, we can also just chat, and if you have a question, feel free to email me, or I don't know, if you see me at CUPS or so, yeah, ask what could be useful for your data analysis, because I think there's a lot of possibilities now.
Definitely. Thank you so much, Daniel. Unfortunately, we're out of time, but recommend definitely reaching out to Daniel if anyone needs help or wants to know more information. That was great for me. So yeah, and then I think with that, feel free to head out, and happy Thanksgiving, everybody. Enjoy your holiday.